So in our lecture about multiple linear regression, we talked about the t-test, which is used to test hypotheses about individual coefficients or even about differences or linear combinations of coefficients. But sometimes we'll run into situations where we want to do a more complicated type of test. And for those situations, there's something called the F test. So let's remind ourselves about the multiple linear model for the data yi. We model lowercase yi with random variable uppercase yi, which is b0 plus sum j equals 1 to p, bj xij plus epsilon I. Now recall that xij is the value of the jth covariate for the ith observation. And then our assumption about the epsilons, or the error terms, is that this collection of random variables all have a normal distribution with the same variance and are independent. So, to review the t-test real quick, we use the t-test for the following type of hypothesis. So H naught hypothesis equals the statement B3 equals 0. So the third regression coefficient is 0. Which is like asking the question, is the third covariate linearly related to the expected response after controlling for all the other covariates in the model? Okay, so that's where the t-test is useful. But let's look at a more complicated scenario. Suppose we have a situation where the response is the height of a child, and we have 6 covariates. The first 2 covariates are the heights of that child's parents. So there's a mother's height and a father's height. And then the next 4 covariates are the heights of that child's biological grandparents. So xi3 is one of the grandparents' heights, xi4 is another, xi5 is another, and xi6 is another. And of course, in this example, we'll want to keep track of which height corresponds to a mother and a father, and which is a grandmother and a grandfather. Okay, so one question you might have about this, and this is potentially a question you would have about any inherited trait. Height is just one example. But the question might be, are grandparent heights linearly related to child heights after controlling for parent heights? So you may have heard some folklore, I don't know if this is folklore or not, that certain traits can skip a generation. So there might be information in the grandparents that's not contained in the information of the parents. So to test this, this hypothesis would be that the coefficients B3, B4, B5, and B6, which are the grandparent coefficients, are all equal to 0. So one way of writing that hypothesis is the following. Another way, which is probably more commonly written, is to say B3 equals B4 equals B5 equals B6 equals 0. So this just means that they're all equal to 0. So for this situation, now you could go and test individual hypotheses, B3 equals 0, and then test with the t-test, and then test the hypothesis B4 equals 0 with a separate t-test, and so on and so forth for B5 and B6. But then you run into additional difficulties, namely dealing with multiple comparisons, and you have to do adjustments, and that all kind of turns out to be a mess. It would be better if you can come up with one test to test this entire hypothesis at the same time. And for that, you can use what's called an F test. So when you think about using an F test, what you're really doing is comparing 2 models, or a pair of models. We refer to these 2 models as the reduced model and the full model. And these 2 models have to have the following relationship. The reduced model must be what's called a special case of the full model. So what I mean by special case is when you look at the full model, you get the reduced model by imposing a restriction on the parameters from the full model. And the particular restriction that you apply is the restriction that's implied by the null hypothesis. So let's see how this works with the grandparent example. So let's look at the full model first. So this is the same model we wrote down before. yi has an intercept and 6 covariates. The first 2 are the parent covariates, and the next 4 are the grandparent covariates. And recall that the null hypothesis is that the grandparent regression coefficients are all 0. So the effect of the grandparents is 0 after controlling for the parents. And the reduced model is precisely the model you get by setting those 4 coefficients to 0. You'll get yi is b0 plus b1 xi1 plus b2 xi2 plus epsilon I. So the reduced model is a special case of the full model, and we get the reduced model by applying the null hypothesis to the full model. So there are other examples where the F-test is used, and if you just start to think about this, this is really powerful. You can write down all sorts of hypotheses and apply them to the full model and get the reduced model, and then use the F-test. There's one caveat that we're not going to dig too deep into here, is that the particular type of hypothesis has to be what's called a linear hypothesis, or that you can write down the hypotheses in terms of a set of linear equations. But we're not going to go into that. All that means is you can't do things like hypothesis that b2 squared equals b1. So we're going to be looking at only linear hypotheses like this. So one of them is that one example is if you take all of the regression coefficients that are not the intercept and set them to 0, if this is your hypothesis. You can do this comparison with an F-test. And this one is so common that when you do the summary command, run the summary function on an LM object in R, it will automatically print out the results of that F-test. So this is kind of the default F-test that R does for you. Another example, so you can impose that 2 of the coefficients are equal, but not necessarily equal to 0 or any particular number. So for example, if you were looking at this model, which just has the parent heights in it, you might consider a model that's a special case of this one, wherein the father height has an equal contribution to the mother height on the child height. Of course, then you'd have to use kind of standardized heights for the 2 parents, because on average the father's heights will be higher. So you can do things like this. You can also do things like this. So hypothesis that b2 equals 0, which, as you recall, you can do this with a t-test. So anything you can do with a t-test, you can also do with an F-test. Just a quick side note, you can do this second one, b1 equals b2, with a t-test as well. All right, so that's enough talk about what the F-test does. Let's look at how it actually works in practice. So it's actually pretty simple. It's not too complicated. So let's go through the steps. So remember, we have these 2 models in mind, the full model and the reduced model. The reduced model has to be a special case of the full model. So the first step is that you fit the full model and you record 2 pieces of information from the full model. The first one is the residual sum of squares from the full model. And the second piece of information is the residual degrees of freedom from the full model. And we'll call those 2 things RSS1 and DF1. The second step is you fit the reduced model and record the same corresponding pieces of information. So RSS0 is the residual sum of squares from the reduced model, and DF0 is the residual degrees of freedom from the reduced model. Then you calculate the F statistic, and here is the formula for the F statistic. It has a numerator and a denominator. In the numerator, you do RSS0 minus RSS1, and then divide that quantity by df0 minus df1. And in the denominator, you do RSS1 over df1. And then the last step is to compare the particular F statistic that you observe, this lowercase f, to what's called an F distribution, which is a probability distribution. That distribution has two parameters, df0. It has a numerator degrees of freedom, which in this case is equal to df0 minus df1, and a denominator degrees of freedom, which is df1. So the F distribution has these two parameters, these two degrees of freedom. And this F statistic, the random version of this F statistic, has an F distribution with these two parameters, df0 minus df1 and df1. All right, so that's the formula. I think it's worthwhile to spend a little bit of time thinking about our intuition for what the quantities in this formula, what they mean and what particular values they can take on. So if we look at df0 and df1, I'm going to claim here that these two are related in a particular way. So what I mean here is one of these three things is true every single time. So either df0 is less than or equal to df1, df0 is equal to df1, or df0 is bigger than or equal to df1. So what I want you to think about is basically I want you to kind of circle one of these three things, either less than, equal, or greater than, and tell me which one is always true. So think about how that works, particularly with respect to what this number means. It's the residual degrees of freedom from the reduced model, which is a special case of the full model. The other thing is that's going to have a consistent relationship are RSS0 and RSS1. So one of these two things is always going to be either less than the other or bigger than the other or equal to the other. So what I'd like you to do is pause the video for 30 seconds, 60 seconds, and think about what the relationship between df0 and df1 is, and what the relationship between RSS0 and RSS1 is. Okay. So let's think through the degrees of freedom first. Now, if the reduced model is a special case of the full model, that means you're kind of taking terms out of the mean part of the full model to get the reduced model, which means you're decreasing the model degrees of freedom, which means you have to increase the residual degrees of freedom. Remember, residual degrees of freedom is just n minus the model degrees of freedom. So let's go through that logic again. To get the reduced model, you decrease the model degrees of freedom, which means you increase the residual degrees of freedom. And therefore, df0 is always going to be bigger than df1. So the residual degrees of freedom in the reduced model is always bigger than the residual degrees of freedom in the full model, which implies that this quantity here, df0 minus df1, is always a positive number. Okay, now let's look at these two relationships. What I'm going to claim is that the residual degrees of freedom from the reduced model is always bigger than the residual degrees of freedom from the full model. So let's look at an example to try to convince you that that's going to be the case. All right, here's our data set, y1 to yn. And in this data set, we have one covariate, xi1. And so our full model is the simple linear model, b0 plus b1 xi1 plus epsilon I. And the reduced model is the model that sets b1 equal to 0. So the reduced model is yi equals b0 plus epsilon I. So this corresponds to the hypothesis b1 equals 0. So we can do this comparison with an f-test. By the way, we can also do it with a t-test, and we've already done that in a previous lecture. So if we look at the quantities that we have to store, df0, this is a typo here, df0 is the residual degrees of freedom from the reduced model, which is this one, which is n minus 1. So that's a typo. This 2 should be a 1. And df1, which is the residual degrees of freedom from the full model, is going to be n minus 2. So this one is correct. That's because the full model has two regression coefficients, b0 and b1, which makes its model degrees of freedom 2, which makes its residual degrees of freedom n minus 2. So just to remind you, this is n minus 1, this is n minus 2. And if we take the difference between these, we get 1. So that reiterates our point that the reduced model residual degrees of freedom is always bigger than the full model residual degrees of freedom. Now, the more complicated aspect is the relationship between the residual sum of squares. So let's look at, I'm going to define this quantity, RSS B0 star B1 star. So this is the formula for the residual sum of squares criterion for the full model. And it has this formula. So B0 star B1 star are the candidates. The way we get B0 hat and B1 hat is we minimize this criterion with respect to these candidates B0 star and B1 star. And the minimizers are B0 hat and B1 hat. And so that's what RSS1 is. So RSS1 is the residual sum of squares from the full model. It's this residual sum of squares criterion evaluated at the minimizers. So this is RSS B0 hat, B1 hat. So this is the minimizer of this function. Now, if we look at RSS0, this is going to be the residual sum of squares for the reduced model evaluated at its minimizer. And if you recall, when we analyzed that model, the minimizer, so the residual sum of squares criterion is going to look like yi minus b0 star squared. And the minimizer, the b0 hat, was equal to y bar. So this quantity here is the minimizer of the residual sum of squares for the reduced model. But if you stare at this quantity, this actually corresponds to the residual sum of squares criterion from the full model, but we're plugging in y bar for b0 star, and we're plugging in 0 for b1 star. So if you were to take this criterion, which is the residual sum of squares criterion for the full model, and you were to plug in b0 star equals y bar and b1 star equals 0, you get the residual sum of squares from the reduced model. So you can just write that out and plug in those numbers and convince yourself that this quantity is equal to this quantity. Now, the fun thing about minimizers is the following fact. So RSS B0 hat B1 hat is the minimizer of this criterion with respect to these two parameters. What that means is that this quantity, this residual sum of squares, is smaller than the residual sum of squares evaluated at any other values of the parameters. In particular, if you were to plug in y bar and 0, this quantity has to be bigger than or equal to this quantity. And since this quantity is RSS1 and this quantity is RSS0, that means the residual sum of squares for the full model has to be smaller than or equal to residual sum of squares from the reduced model. Now, if we look at the quantity that appears in the statistic, it's RSS0 minus RSS1. So since this thing, RSS0 is bigger than this thing, that means this is also a positive number. So the numerator is a positive number. And what this quantity measures, RSS0 minus RSS1, this is how much the residual sum of squares goes down when you switch from the reduced model to the full model. So this is often called the reduction in sum of squares under the full model relative to the reduced model. This thing if you look at this quantity and write it out in terms of the model degrees of freedom, remember df0 is n minus the model degrees of freedom from the reduced model. And df1 is n minus the model degrees of freedom from the full model. The n's will cancel, and what you get is mdof1 minus mdof0. So if you try to interpret this quantity, what it is this is how much the complexity of the model increases when you switch from the reduced model to the full model. So in this particular example, you get one extra parameter, so the complexity of the model increases by one parameter. In the grandparent example, this would be 4. It increases by adding 4 parameters. So this number, df0 minus df1, you can think of as a measure of the increase in the model complexity. Now, the term that appears in the denominator of the F statistic is RSS1 divided by df1. And if you recall, this is just the estimate of sigma squared from the full model. You take the residual sum of squares, you divide by the residual degrees of freedom. So all of these quantities that appear in the F statistic have an interpretation. The reduction in sum of squares, the increase in model complexity, and the estimate of the variance parameter in the full model. All right, so let's wrap this up. Let's really quickly go back to the statistic. What the F-test is measuring, you take the reduction in sum of squares, you scale it by the increase in model complexity, and then you scale that whole thing by an estimate of sigma squared. So let's just reiterate this. F statistic is going to be a positive number because everything in there is a positive number. The numerator is the reduction in sum of squares scaled by the increase in model complexity. The denominator is an estimate of the variance. The purpose of this is that it makes the F statistic a unitless quantity. What I mean by that is you'll get the same exact F statistic if you were to measure heights in centimeters versus heights in inches. So this is a convenient thing. It makes the results of your test not depend on what the units you measured things in, which is a good thing. So we're taking the reduction in sum of squares scaled by the increase in model complexity, and we're scaling that by an estimate of the variance to make it a unitless quantity. So that's how things work in theory. In R, we'll practice computing these sum of squares quantities just so you can see what's going on. But in R, you can do all of this with the ANOVA function, and we'll show you how that works as well. By the way, ANOVA is short for analysis of variance. So you'll hear that term a lot, ANOVA, or analysis of variance. All that means is you're doing an F-test. The reason that term is used is because the F-test depends on residual sum of squares quantities, which are used to estimate variances.